Hi and welcome to this video about process enumeration, the second part. In the first part, we've seen various enumeration APIs that are provided by the Windows API. We've seen the tool help functions, the Windows Terminal Services API, and the bare minimum enum processes API. Then there's another option, at least one, using the function anti-query system information, which is only partially documented being part of the Windows native API. That's the API implemented by NTDLL. So first, how do you get these native API definitions? The best source for this API is the PHNT or the Process Hacker NT project that is currently hosted on GitHub in this address. And so when you go to this project, you can go ahead and download the header files and just copy them to your project directory that you're building with Visual Studio, say. However, there's a better way if you intend to use this API in several projects. You can use VC Package. VC Package is a C++ package manager provided by Microsoft. And in fact, if you have that already installed, you just need these two lines in order to install the PHNT library. The first one is just used to make sure that VC Package is integrated with Visual Studio. If you don't have VC Package installed, just go ahead, look it up on GitHub and follow the simple instructions to install VC Package on your machine. And so for where you have that installed, you can use these two command line strings that you can see here in order to install PHNT. In general, the native API is a very broad topic which I'm now writing a book on. You can find that on libpub.com, and if you buy the book, all updates are free. Currently, there are 4 chapters there at the time of this recording. So let's see how to work with the native API and get more information about processes than is available with the other APIs that we've seen. Okay, so going back to Visual Studio, this was our previous project. So now let's add another one to this solution. I'm going to right click, add another C++ simple project, console application. Let's call that antiproc list just to make it nicer. And the first thing we need to do is to get the headers for PHNT. Now, since the headers already been installed on my system using VC Package, this is what we need to do. We need to add 2 includes in this order, PHNT Windows and then PHNT, and that's all there is to it. In terms of includes at the very least. Let me add some stuff here like stdio. I'm also going to use perhaps a class from the C++ standard library that is part of the memory header. So now what we want to do is to enumerate processes. So how do we do that? So we have this master function, in fact, called anti-query system information. And this function provides lots of capabilities, but we're going to focus on process enumeration only, and even just a subset of that, because there are actually several ways to perform this enumeration. So first I'm going to need a buffer here. So I'm going to use the unique pointer class to have a buffer that's going to hold onto the data returned by the API. At this point I don't really know how many bytes I'm going to need, so I have to ask the API. I'm going to call anti-query system information. This is a generic API. We need to provide various information classes. So this is just an enum that you need to provide. In this case, what we need is system process information. This is one of those that provides information about processes. Then we need to provide a pointer to a buffer, which we currently don't have, and the size, which is currently going to be set as 0, and we're going to get back the size back as the last argument here. So while the status that we get here is going to be status length mismatch or something, so we need to make sure that the length is correct. So we have info length mismatch, and that's always going to be the first result here because the buffer is 0, which of course is not a valid size. Then we can go ahead and make the allocation here by using make unique here, for example, and allocating a buffer with the size provided as a result here in this size variable here. So that's the point. Of course, we don't have to initialize size here to 0, but sometimes I like to initialize things just for the sake of it. And then we can make the same call again. So let me copy that. So of course the status, we're going to leave that variable here. And now we do have a buffer on our hands. So we have the buffer pointer here, and we have the size that we need to provide. So obviously I've put it in the wrong location. So right in this way. And in fact, before I do that, I'm going to increase size by some factor. Say, let's add 4096, like more 4K bytes more. Why? Because between the time we call this function and actually call the function a second time, maybe another process or processes will become created. They will just be there, and that would require even more memory. So we have a chance here not to call this function too many times, because if then processors would be created, this function return again status info length mismatch. I will have to reallocate a size. So it just makes it less likely to require reallocation the second time around. So once we get out of this loop, assuming that we get okay, and of course we can check that, well, we could do something like this, make sure that the status is success when it's above 0 or higher. If not, let's just exit the application. So now we can move forward into actually performing the enumeration. And if you look at the header file itself in system processing information, the header file provided by PHNT, you can see here the associated structure that is expected to be retrieved here, which is system process information. So I'm going to take advantage of that and do something like this. I'm going to cast the buffer that I have to this pointer. And now we can start actually doing something with this pointer. So this pointer would point first to the first process in line. So if I go with P arrow here, we can see all the list of lots of properties that are available for a process, meaning more than we've seen in the normal Windows API. We can of course look at the structure itself. In fact, there are some other information classes that provide even more information about each and every process. So you can see lots of stuff here. And let me just grab some of them just to make it more concrete, and we'll display that information. So let's go ahead and use a printf here. Let's start with the process ID, which is probably the most fundamental piece that we have. We have also the parent process ID. Let's grab it as well. Let's take number of threads here that should be available here as well. Do something like this. And then, of course, we have the name, wanted to provide the name of the executable or some kind of path. So let's call that, let's call that path, or let's just use name and provide something here. We'll see in a moment whether what I'm writing here is correct or not. Maybe there's some other pieces of information here that might be interesting. Let's take a look, maybe grab something else, such as, say, the handle count and session ID. Let's take that as well. So we have handle count, let's add that here. That's number of handles. And then we have the session. So let's do that as S and use something like this. And we have a name. Let's assume that's enough for now. Let's get the parameters here. So first we need to create the process ID. That's in the unique process ID member here. So it might seem simple enough. However, if you look at the member itself, it actually is typed as a handle. Does that mean it's actually a handle to a process? No, it's actually an ID. And the reason for that is because internally within the kernel, process IDs are actually generated from a private handle table. So the type is handle, but it actually means ID. So we need to just convert that to a ulong just to make it easier to display a simple number. This just performs some casting, doesn't do anything significant here. Simply does some casting, which I can do myself, by the way, by doing something like maybe casting that to ulong. And before I do that, I have to cast that to long pointer, which means a ulong in the size of a pointer, just to make the compiler happy. So using handle to ulong is, I would say, a bit more elegant than performing the casting yourself. The same idea goes with the parent process ID, and this is coming from this weirdly named member inherited from unique process ID. So we have the process ID of the parent, and then we have number of threads. Okay, let's go with that. So we have number of threads, and then we have the number of handles. So that would be handle count, and then we have the session ID, and then we have the name. So the name is provided using this member called image name. In fact, image name, if you look at that, it's actually something called a Unicode string, which is a very typical data structure used within the native API and the kernel itself for holding on to strings. So in fact, this is a string descriptor that has a pointer to the beginning of the string and the length. That's the basic gist here, and that's why I'm using WZ here. This is the correct specifier to use for a Unicode string, because the string internally doesn't have to be null terminated, in fact. And that's all I'm going to do for now. Now we need to go to the next process, and since the size of every process structure is dynamic, because each one has its own name, there's a member here called next process or next entry offset, which represents number of bytes we have to add in order to get to the details for the next process. If it's 0, it means we're done. No more processes exist in the list. Otherwise, we want to move forward. So the way to do that is to grab the existing pointer. Let's perform some casting here at the end. We need to grab the existing pointer here and add what next entry offset says. And so the important point here is to cast the pointer p to a pointer to a byte. Why? So that this addition would happen in units of bytes. Otherwise, if we don't do that, the C language rules state that the addition here is in the number times the size of whatever p points to. So we have to be careful here. We have to add as a number of bytes, and that's why I'm using that as a pointer to a byte. And that's essentially it. This is all we need to do in order to get the list of processes with quite a few details, in fact. And I've just looked at some members, but as you can see, there's lots of more members there to look at. And of course, we get an error here. Well, not of course, perhaps, but we do get an error because the linker is unhappy. The linker sees the function anti-query system information, but doesn't see any implementation for that function. So we have to add that as a dependency. So I'm going to use another pragma here to add that as dependency without going into the project properties. So in fact, the import library or some part of import library for NTDLL does exist and is provided by Microsoft with Visual Studio Tools. It simply is not added by default to the list of imports in a typical project. Only the standard Windows API DLLs, import DLLs or import libraries are being added. So now that we do that, the code compiles. I can go ahead and make this the startup project, press Ctrl F5, and we can see everything that we expect to see here. So it starts with these special names for processes such as system, secure system, the registry process. Then you can see here executable names here. So it's actually pretty apt what I've written here. Notice that the system idle process doesn't really have a name associated with it, and this API doesn't return any kind of name for that. So it's actually a null pointer there, which is how it's displayed with a %WZ specifier. So you can see all the processes here as we expect. And these APIs, by the way, are used by Process Explorer and Task Manager to get process information, because as part of that, not just because of the fact it gets so many details with a single call, but also because system process information also provides a view into the threads of the process, again with various degree of detail based on the exact information class you select. There are 3 of them you can work with. I've shown you the simplest one, but there are 2 others that are available: system extended process information and system full process information, which provide even more details as to the process and the threads. Now, one thing you might find that is missing with all these APIs and all these enumeration APIs and structures is that you don't find the command line for the process in question. And the reason is that there's lots of details for a process, and putting everything in that call would make the call relatively slow. And so if you want to get to the command line, in fact, you'll have to open a handle to the requested process and use different APIs to obtain the command line. And maybe we'll see that in a different video.